Welcome again to the tutorials on dynamic system modeling and control. Once again, my name's Hossein Fethi, and it's great that you're joining me on these tutorials. The purpose of this particular tutorial is to explain and highlight the notion of equilibrium in a dynamic system. So to explain the concept of dynamic system equilibrium. This tutorial plays a very interesting role in this overall set of tutorials in that it marks the transition from modeling to analysis. So at this point we are basically done with the tutorials on how to build dynamic system models, and the next thing we're doing today or in this tutorial is to illustrate how we can take a dynamic system model and use it to try to understand the system a little better, understand the system's properties and behavior a little better. So there are three specific goals for this tutorial. First of all, you've already seen the concept of equilibrium in previous classes, whether thermodynamics or chemistry or other courses, mechanics. You've heard the word equilibrium many times before. And so what I want to do is I want to illustrate a few examples of what it means for a dynamic system to be in equilibrium. I want to present a few illustrative examples of that. And the reason I want to do that is because the concept of equilibrium in system dynamics generalizes all of the concepts of equilibrium that you've seen in all of your previous studies. I want to draw a general definition of dynamic system equilibrium from all of the above examples. That's the second goal. The third goal, there are two very particular specific caveats regarding the definition of dynamic system equilibrium that I want to highlight. Specifically, I want to explain the notion of a zero input equilibrium, and I also want to explain the notion of a reference equilibrium. So with that in mind, the first goal, as I said, is to present a few illustrative examples of dynamic systems that are in equilibrium. So let's start with the simplest example I'll share with you today, which is a body in motion. So I want to think of a point mass M, and there are forces acting on this point mass in, let's say, a two-dimensional world. And we know from Newton's laws of motion that a body in motion remains in motion at a constant velocity if the sum of all the forces acting on it is zero. And we call that an equilibrium. So to rephrase that a little bit, this body is in equilibrium if, number one, the net force acting on it is zero, and as a consequence, perhaps more importantly, number two, its velocity is constant with respect to time. So that's an equilibrium from the world of mechanics. Now let's move to an equilibrium from the world of thermodynamics. Namely, let's examine a cup of hot water. So you have a little cup here. This image is from the Microsoft Clip Art library. And there's hot water in the cup. The cup loses hot water through evaporation to the surrounding atmospheric environment. It is, however, possible that some of the moisture from that environment condensates back into the cup. And you can imagine a situation where this cup is in equilibrium, meaning that the evaporation and condensation rates are equal. This could happen, for example, if you're trying to drink hot water or hot tea in a sauna. The surrounding humidity might be high enough for water to just not have a net evaporation rate. And that's basically the concept of equilibrium from thermodynamics. We say that this cup is in equilibrium if, number one, the evaporation and condensation rates are equal. Number two, as a consequence of that, and perhaps more importantly, the amount of hot water in the cup remains constant with time. Now, the third example I want to share with you comes from the world of chemistry. So you can, speaking of water, you can have a container that is full of water, and you drop a little lump of table salt into that container, and given enough time, the table salt will begin to dissolve in the water, and at some point you will reach an equilibrium where the table salt is no longer dissolving in the water. And the question is, what is happening at this equilibrium? Well, what's happening in general is that the table salt, sodium chloride, is dissociating and dissolving in the water and breaking up into sodium ions and chloride ions. And at some point, you begin to see the sodium and chloride ions are recombining to form sodium chloride and precipitating in the form of sodium chloride. These two processes are chemical reactions. There is a dissolving reaction or a dissolution reaction, and then there is a precipitation process that is also a chemical reaction. And both of them are happening at the same time. When you're in equilibrium, the forward reaction and the backward reaction are happening at the same rate, so that sodium chloride in solid form and sodium chloride in aqueous form are now both constant in terms of amount, because the system is in equilibrium. So again, the system is in equilibrium if the forward and backward reaction rates are equal. And as a consequence of that, and perhaps more importantly, the amount of salt dissolved in the water and or the amount of undissolved salt, both of these are constant with respect to time. You notice that in all of these examples, there is something that looks like a system state. Velocity of a mass, amount of hot water in a cup, amount of dissolved salt in a salt water solution, and whatever this quantity is that looks like a system state, that quantity remains constant with respect to time. It wouldn't be constant with respect to time if the forces acting on the system, causing the system to change, causing the state of the system to change, if those forces were not balanced. But the important thing about an equilibrium is that the state of the system in equilibrium does not change. So this leads me to the second goal for this tutorial. Now that I've presented just a couple of illustrative examples of dynamic systems in equilibrium, now I want to draw a general definition of dynamic system equilibrium from the above examples. And unlike the above examples where I was very informal in my presentation, now we're going to present the definition of an equilibrium fairly formally using mathematics. So when is a dynamic system in equilibrium? What I want you to do is to consider a dynamic system governed by the state space model we've been exploring in all of these tutorials. X dot is f of x in u, and y is equal to g of x in u. And I want you to consider a point. And here is exactly what I mean by a point. A value of the state vector x naught, a value of the input vector u naught, and a value of the output vector y naught. And if I wanted to be very, very precise in my use of mathematical language, I would say that this is a tuple. It's a set of values of x, u, and y all together rolled into one definition of one point. What I'm going to say is that this point is an equilibrium point if the rate of change of the system state at this point is equal to 0. In other words, x dot is equal to 0, which means that f of x naught and u naught is equal to 0, but the output equation still applies, which means y naught is equal to g of x naught and u naught. If these equations are satisfied, then the point x naught, u naught, y naught is an equilibrium point. Now I want you to note a couple of things. First of all, the equilibrium point satisfies the system's dynamics. I basically took x dot is equal to f of x and u, substituted 0 for x dot, meaning I don't want to see any change, okay? But the rest of the set of state space equations is the same. So an equilibrium point is a point that satisfies the dynamics of the system that it describes. And the second thing I want you to notice is that if you take this dynamic system and you initialize it exactly at equilibrium, it will remain there forever, okay? So if I were to take the system and put it exactly at a state x naught and apply an input on it equal to exactly u naught and see an output of exactly y naught, and if I were to hold that input in perpetuity at u naught, the system should not change, the state should not change, x dot will always be 0. The operating word here that is very important is exactly, okay? We will see later on in these tutorials that the system may experience non-trivial change if you initialize it slightly off from equilibrium. If you perturb the system from equilibrium a little bit, it may actually have some dynamics that are interesting. But if you take a dynamic system and you initialize it perfectly at equilibrium, it remains there indefinitely. The second thing I want you to notice once again is the fact that the values of the system states, inputs, and output variables all appear in the definition of an equilibrium point. So even though I'm calling it a point, it's not a point just in the state space or in the input space. It's a point in the state, input, and output spaces, and that's my definition of an equilibrium. Okay, and that's generally the community's definition of an equilibrium, although this is a nice way to segue into the next goal for this tutorial, which is to sort of be a little more careful about some of the caveats associated with this definition vis-a-vis some of the other definitions of equilibrium that appear in the literature. So now moving on to the third goal, which is to highlight the notions of a zero input equilibrium and also a reference equilibrium. So there are two important things that I want you to keep in mind. Remember, in the definition of an equilibrium that we just went through, the input U naught can be anything. So in general, an equilibrium point for a dynamic system can involve a constant but non-zero input. A zero input equilibrium is a very specific equilibrium point, and a system can have one or more of these, where the input U naught is exactly equal to zero. Okay, so I'm restricting my definition of an equilibrium even further here, and I'm saying I'm only interested in those equilibria that correspond to zero input. The reason why I'm highlighting this definition is the following. A lot of the time when you study system dynamics and you open a textbook on dynamic system modeling and control and you look at the textbook's definition of equilibrium, what the textbook is really presenting to you is the definition of a zero input equilibrium. Okay, so I want to make this distinction, as you know, because it's important to keep it in mind as you read references on this subject. The term equilibrium point in the dynamic systems literature sometimes refers implicitly to a zero input equilibrium point, and so you need to be careful about that when you read textbooks on the subject, standard textbooks on the subject. The definition that I'm presenting in these slides is more general than a lot of the textbook definitions, okay? And you just need to be careful about that. The second important caveat is this. A system, as we're going to see in the next tutorial, may have no equilibria, one equilibrium, 2, 10, 100, a million, an infinite number of equilibria. Very often there's one particular equilibrium that we want to operate the system at that happens to be desirable for some reason or another. We will refer to that as a reference equilibrium. So a reference equilibrium is a particular equilibrium point that one would ideally like the given dynamic system to operate at. Okay? In some textbooks and references, the word reference or the expression reference equilibrium is replaced with nominal operating points. So some textbooks will talk about nominal operating points, and that's essentially the same as a reference equilibrium. So what have we done in this tutorial? We've presented a few illustrative examples of dynamic systems that are in equilibrium. We've used these examples to draw a general definition of equilibrium, and we've just highlighted a couple of caveats regarding what is a zero input equilibrium and what is a reference equilibrium. What I would like to do in the next tutorial is to basically go over a couple of examples of how to determine the set of equilibria for a dynamic system. And one particularly critical question in that context is how many equilibria does a given system have anyway? If I give you a dynamic system, does it have no equilibria, 1, 2, 3, 100, a million, an infinite number? That turns out to be a very interesting question. And it turns out that depending on the system, all of these are legitimate possibilities. A system can have no equilibria at all, or a finite number of equilibria, or an infinite number of equilibria. So that we will cover in the next tutorial. Thank you very much for watching and listening to this tutorial, and I look forward to the next one.